Okay guys, this is number 2. So we have a 5 ampere current source, 7.2, 30, 6, 64, 10, and we are asked to look for the value of V. V is actually the voltage across our current source. And then we're going to get also the power delivered by the 5 ampere source. And then we're going to get the individual currents, the individual powers dissipated by each of the resistors. So it's like we're gonna perform power check, and we have to get all the currents in each resistor through each resistor in order for us to be able to get the power dissipated by each. Okay, so let us start. We know that V is I times R, right? So V is the V total, and I total is 5 amperes, and then our total is, we're going to combine all of the resistors here into a single resistor. So by series parallel connection of resistors, we can combine all of them. So 6 and 10, they're in series, so 6 times 10 is 6 plus 10 is 16. And then 16 is in parallel with 64. Why? Because they have the same terminal, set of terminals. So let us do that. 16 times 64 divided by 16 plus 64. So the answer here is 12.8. And 12.8, the combination of the three resistors, and then series with 7.2. So plus 7.2 plus 7.2. The answer is 20, and 20, all of these is represented by 20. Then they're in parallel with 30. So 20 times 30 divided by 20 plus 30. The answer is 12. 12. So our R total, guys, is actually, by combining all the resistors, 12 ohms. So we cannot get the value of V. So our VT, therefore, or the V equals the V is, what is I total? 5 amperes, and then the R total is 12. So the answer is 60 volts. So V is 60 volts. So we were able to get the value of V already. 60 volts. And then power by our delivered by our 5 ampere source. So power 5 amperes is its voltage, which is 60, times its current, which is 5. The answer is 3. 5 times 6 is 30, 300 watts. Of course, this is delivering. So we got the value of the power delivered by our current source. Next, power in each of the resistor. So to get the power in each resistor, then we should be able to get the current here. Let's call this I1, and then the current here, I2, then the current here, I3, then the current here, I4. So we are in circuit reduction. So to be able to get for the value of I4 and I3, so we have to combine all of these into a single resistor. And we said that 16 in parallel with 64 is 12.8, and then in series with 7.2 is 20. So our circuit now will become like this. This is our 30. And the 7.2 plus 12.8 is 20. Okay. And then of course, our current here is 5 amperes. The current, total current, right? 5 amperes. So this is now our I1, I4. And then the current here is I3. So by CDP, we can now get the value of I1 and I4 and I3. So if you're going to get I3, IS, what is our IS is 5. The current flowing towards this node divided by two currents, right? Divided into two currents. So 5 times what is on the numerator? If this is I3, then the numerator should be the 30, the opposite one. So this is 30 plus 20. So I3 therefore equals 5 times 30, 5 times 30 divided by 30 plus 20. 30 plus 20. The answer is 3. 3 amperes. And then, if you want to get I4, then I4, this one. So 5 again, IS. And then, what is on the numerator should be 20. And then this is still 30 plus 20. So what is I4? Therefore, the answer is 5 times 20. 5 times 20 divided by 30 plus 20 or 50. The answer is 2. 2 amperes. So I3 and I4 we were able to get already. So the next is I2 and I1. So the current flowing through this node again is I3. What is I3? 3 amperes. And this one is I2, and the current flowing through this branch is I1. So if you're going to redraw our circuit, so this is our 64, and then this is our, what is 6 and 10? 16. What is the current flowing towards the nodes, the node connecting them? This is I3. I3, which is equivalent to 3 amperes. So this is now our I2, and this is now our I1. So by current division principle, we can now get their values again. So let us get their values. So what is for example, I2? Of course, the current flowing through this node, which is 3 amperes or I3. What is on the numerator? If we're going to get this I2, the numerator should be 16, the opposite. So 16 plus 64. And I2 therefore becomes 3 times 16 divided by 16 plus 64. The answer is 0.6. Let us check again. 3 times 16 divided by 16 plus 64. 0.6. So this is 0.6 amperes. Now let us get I1. I1 is, of course, the current flowing towards the node that connects them. So 3, and then this is 64, and this is 16 plus 64 still. So our I1 equals, this should be 2.8. 3 times 64 divided by 16 plus 64. Answer is 2.4. 2.4, that's correct. 2.4 amperes. So if you're going to perform KCL, look 3 going in and then going out are 0.6 and 2.4, and our KCL is satisfied. Now let us get now the values for the powers. Let's start with the 30 ohms. So power dissipated by the 30 ohms What is that? I4. What is I4? 2 amperes. So that is 2 squared times 30. The answer is 4 times 30 is 120 watts. Of course, absorbing. And then let us power 7.2. Power 7.2 is I3. Where is I3? 3 amperes. So 3 squared times 7.2. The answer is 9 times 7.2. 9 times 7.2. The answer is 64.8 watts. 64.8 watts. This is still absorbing. Then power 64 ohms. Absorbed by 64 ohms. What is the current flowing through 64? I2, so 0.6. So 0.6 squared times 64. The answer is 0.6 squared times 64. 23.04. 23.04 watts, still absorbing. And then power 6 and 10. Can we just put that power 16 ohms? Current flowing through them is I1, which is 2.4. So this is 2.4 squared times 16. So the answer is 2.4 squared times 16. 92.16. 92.16 watts, still absorbing. Now let us check if power absorbed equals power delivered. Power delivered is 3,000, which is the power delivered by the 5 amperes. Power absorbed therefore equals, let us all the resistors, 92.16 plus 23.04 and then plus 64.8 plus 120, and the answer is 300 watts. The same. So our power check has been satisfied.